progress, I believe. Mic check 1, 2, 3. Mic is good. Audio is good. Okay. So this question, I'm going to read the question so it'll be easier for you to watch it again. We have 7.46 grams of potassium chloride, which is dissolved in 100 milliliters of water, and we're given an initial temperature over here, right? Our initial temperature is 24.1 degrees Celsius. The final temperature of the solution is 20.0 degrees Celsius. The question is, what is the molar enthalpy of the solution of potassium chloride? Okay. Let's start with what is given to us, okay? So let's identify all the information from this question, which gives us information that you can use later on, okay? So tell me, let's start the question. It says 7.46 grams of potassium chloride is dissolved in 100 milliliters of water. What's the given over here? Potassium chloride. What about potassium chloride is given to us? What is that 7.46? Right? Think about units, right? Think about symbols, right? Yeah, okay. So the unit over here is grams, which means the symbol should be. What does gram represent? Mass is the mass, right? How much mass of potassium chloride do we have? Right? We're given that. What's the symbol for mass? Upper or lower? Smaller, right? So we have the lowercase m of KCl, and that is given as 7.46 grams. Fantastic. It says it is going to be dissolved in 100 milliliters of water. Now, this is the first time that you're seeing something like this, so I'm going to tell you guys this information. In the future, you will have to do this yourself, okay? If you remember, one of the notes that we have made, the assumptions that we have made in our calorimetry is that even if we have an aqueous solution, right? What are we assuming about that? What do you guys remember? What is the assumption that's made about the aqueous solution? Yeah.
25 degrees Celsius.
No, that's you're thinking standardization, right? I'm not talking about standard over here. I'm talking about calorimetry. We assume that the aqueous solution acts like. So before you answer that question, think about this, right? Let's say I have a cup. Right? Let's say I have a beaker. Okay? Inside this beaker, I have 7.46 grams of KCl, which I'm dissolving in 100 milliliters of water. Right? Can I say that what I have inside this is KCl aqueous? Can I say that? KCl aqueous? Yes, I can say that, right? Because what is aqueous? Right? An aqueous solution is essentially mainly water, but we have ions dissociated inside that water. That is essentially an aqueous solution, right? The assumption that we're making in calorimetry is that even if you have an aqueous solution, because it is predominantly just water, right? We're going to use the specs of water to make our calculations, right? So one of the important specs of water is that it has a density of, anybody? Keep going. 1. What's the density?
1, just 1.
1 what?
1 gram
Per
milliliter.
Milliliter, right? For every 1 milliliter you have, we're gonna assume that that is equal to 1 gram. Make sense? That's the density, right? So even if we have different aqueous solutions over here, right, we're gonna assume that it has the same density as water. So keeping that in mind, right, this aqueous solution has a volume of 100 milliliters, right? And 1 gram is for 1 milliliter. So if I have 100 milliliters, how many grams would that be? 100 grams. Does that make sense or no? Was that confusing or was that okay? Let me just make sure it's frozen over here. Okay. Okay, so far, guys? All right, so what else do I have over here then? Right, I have the mass of water. Right, the mass of water is equal to 100 grams, right? So even if I'm given 100 milliliters, right, I'm assuming that it has a density of 1 gram per milliliter. So that means 100 milliliters get converted into 100 grams, right? Why was this important? Because think about what's happening over here, right? It's a calorimetry question, right? So imagine I have this calorimeter with the double cup, right? The double styrofoam insulations over here with a thermometer going inside it, right? Then a stirring rod, and it has stuff inside it. Right? What's this part over here?
System.
Yeah, no, it's not a system. System is something else in here. Right? What's this stuff? What's the solution part? The system is inside the surrounding, right? The surrounding is encompassing the system over here. Right? So the water is the surrounding. It's a surrounding, right? It is surrounding all the KCl formula units, essentially. Right? Ions, essentially. Okay. So this water, right, that we have, it's going to be at an initial temperature of 24 degrees Celsius. What do I have? Ti or T1. Right? Ti is equal to 24.1 degrees Celsius. Awesome. What else do we have? The final temperature of the solution is 20 degrees Celsius, right? So we have TF. Nope. Get out of here. Fahrenheit? Nope. Degrees Celsius. 20 degrees Celsius. Now, before we even go forward, right, let's do some inferences over here. Our water started at 24.1 degrees Celsius. Remember, water is a surrounding, right? So imagine this, right? There's stuff over here, right? The KCl, essentially, right? The KCl, which is inside this water, right? But the water is the surrounding part over here, correct? Yes? Okay, so far? Right? So let's think about it, right? This water started at 24.1 degrees Celsius. It became 20 degrees Celsius, right? Is the temperature increasing or decreasing? Decreasing. Now, if the temperature of the surrounding is decreasing, right, what's happening to the system?
It's endothermic.
The system must be endothermic. Right? The system is endothermic. It means it's going to absorb. Yeah, right? It's going to absorb heat. Does that make sense? Okay, so far? Everybody? Right? So just keep that in mind, right? So let's see. What we can do over here, what else is given us to us? What is the molar enthalpy? Molar enthalpy of the solution of potassium chloride. Is there anything else that is given to me, or is that it?
Yeah.
That's it? Anybody else think of any otherwise?
No,
That's it? Okay, sweet. So that is our given. What is our ask? What is the to find? What am I looking for over here?
molar enthalpy of the.
Okay, how do I write that down in terms of the symbols and units and stuff?
Delta H, not zero, yes, delta H Rx in mole per KCl.
Rxn, but in this case, we're being specific, right? What's the reaction?
This,
It's a KCl.
What's up? It's a what reaction? Potassium chloride, right? Potassium chloride, what's happening to potassium chloride?
decomposition.
Decomposition? Not quite. We're not decomposing it, right? What does decomposition mean? I mean, you're kind of right, but like there's a specific word that we're looking for over here, right? We're starting with some grams of KCl. We're putting it inside water. What happens to KCl? It dissolves. So So if it is a dissolving, right, what's the name of that solution? I mean, what is the name of the reaction? Yeah, it's a solubility, right? It's a enthalpy of salt.
What? Okay.
I mean, you can write Rxn too, that's okay. But this is like, we're being more specific over here, right?
Okay.
Okay, so far?
Yes.
Any questions?
Enthalpy of reaction. It's still a reaction.
So again, it's still a reaction, right? I mean, it's a physical, right? It's a physical thing that's happening over here. Like we're not really, yeah, you can say reaction. That's fine. You can say reaction. So this right here is a enthalpy of solution, right? We're creating a solution over here, right? So this is essentially what we're looking for. But then be careful, right? We're looking for the molar enthalpy of this particular thing. What does that mean? What should the units be over here?
kJ per mole.
kJ per mole. kJ per kilojoules per moles. Sweet. I know, right? I wish we had the thing again. You guys wrote it down, no?
Yes.
Yes, you did. So if you have that, you can keep that on open right now if you want to. All right, so that's what we want to find over here. Now, let's think about this as a calorimetry, right? We have information about the surrounding, right? So I'm gonna break it down into two different things over here. So we have the surrounding information. Right, surrounding information, and we have some information about the system as well. And we know that the system and surrounding are somehow related, right? What's the relationship? How are they related to each other?
Delta E system equals to delta E surrounding.
E is too broad.
Negative. Okay.
We're thinking about not all energies, but heat. Right, so heat of the system is
equals to negative.
Negative, right? It's the opposite of the heat of the surrounding, right? So we know Q system is negative Q surrounding. Any questions about this, guys, so far? Are we okay?
Is it in terms of temperature or?
Q is heat. There's a formula, right? There's a formula for Q. What is the formula for Q?
Q equals to MC delta T.
Yes, Q is equal to M times C times delta T. Let's think about it. Do we have the mass of KCl?
Yes.
Yes, we do. Do we have the specific heat capacity of KCl? We don't, but maybe we could potentially find it, right? It could be a reference table that we can use. Sure. But what about the temperature change?
We have.
Where is it?
Yeah.
What? Read that for me. What does it say? Say again? Initial and minus. But the question is, when you were doing this calculation, right? So what did you use in the calorimeter? What did you use to figure out what your initial temperature is and what your final temperature is? What tool was used over here? The thermometer, right? The thermometer is dipped inside what?
The solution.
What is the solution in this case? Water, right? So when you are dipping the thermometer inside the solution, which is water, it's measuring the temperature change of water. Right? KCl is just floating around, sure, but how do you measure the temperature change of something that's just flowing around? Right? The temperature change is for the surrounding. Remember, the whole point of calorimeter is to use what happens to the surrounding to figure out what happens to the system. It's an indirect method of calculating the molar enthalpy. Right? Right? So let's do that over here. Right? So what we're given is the M We know the C, right? We know the C of H2O, right? What is that C of H2O?
4.184
Keep going.
J per
Joules per.
gram per Celsius degree.
Correct, right? So joules per grams degree Celsius, right? So we have the mass, we have the C, we can figure out the delta T over here, right? So let's do that first, right? Step one, for the surroundings over here. For the surrounding, the temperature change is going to be equal to, can somebody tell me the equation for that?
TF minus TR.
Right? TF minus TI. What do I get? Equals?
Negative 4.1.
Let's do this, show the proper word, right? So 20 degrees Celsius minus 24.1 degrees Celsius, and that becomes equal to
Negative 4.1.
negative
4.1.
4.1 degree Celsius. Everybody okay so far? Yeah? Any questions?
There is a typo.
Typo? Tell me.
There should be TI, not FI.
Sorry.
Sorry.
TI. Right, so we have our temperature change over here, right? And I can use that temperature change, the mass, and the specific heat capacity to figure out the Q of the surrounding. Yes? Everybody okay? In this case, tell me. Mass times C times delta T, which is equal to, what is the mass given to us over here?
100 grams.
100 grams.
1,000 grams.
We're going to multiply that by
4.184.
4.184 joules per grams times degrees Celsius. Multiply that by, no, not 4.1, negative 4.1. The negative is very important, right? Degree Celsius. I'm going to put that in bracket. Okay, well, let's look at the units over here, right? The grams get cancelled out, the degree Celsius get cancelled out. Right? We're going to be left with just joules.
1715.
Should I trust you?
Trust me.
Trust you? All right, I'll trust you. Tell me.
1715.44.
Nope. Check it again.
It's kg.
Huh?
It had to be J, right?
It has to be joules, but more importantly, it has to be something else too.
Oh, negative 1715. You should trust me.
Negative. I tried trusting you, but then you give me you forgot the negative.
Okay.
Negative 1715.44 joules. All right, sweet. So this is the heat of the surrounding, correct? Well, what does that mean? How can I use that information? Yeah, how can I use that information?
Then we can know Q system.
Yes, we can know the Q system over here. Q system should be equal to what?
Equals to negative Q. Sorry, yes.
I'm just showing all the work over here, right? So the Q system is equal to negative Q surrounding. And that means the Q system should be equal to what?
1715.44.
1715.44 joules. All right, sweet. So we know now that the system over here, right? So the reaction essentially that happened, right? The solution or solubility reaction that happened over here, right? That has the heat that much, right? It absorbs that much heat. But that's not what the question's asking for. Right? The question's asking for enthalpy, which is kilojoules per mole. How do I find that?
We can get the mole of KCl by, yes.
Okay, so let's do that. I'm gonna just erase this over here so I can get more space. This is number 4 now. Right, so what we know is the mass of KCl, which is equal to 7.46 grams, but we don't want mass, right? We want moles over here, right? I have mass, I want moles. What do I need? How do I go from mass to moles, guys? Molar mass. What is the molar mass of KCl?
Forgot.
Use the table. Tell me, guys, tell me.
Let me check.
Just a fair warning, guys. What I'm writing over here, it may not be visible on the video, but I am saying it out loud too, right? So just match it along with that, okay? Yeah.
It's 74.446.
74.446?
Yes.
74.45 grams per mole. I'm not rounding over there, right? So basically, molar mass, we use 2 decimal places always. Okay? So molar mass of KCl, 74.45 grams per mole. And let's use our pyramid. Capital M, lowercase m, lowercase m. Right. So I have mass, I have molar mass, I want moles. What will I do? Divide or multiply? Divide. Divide what with what? Correct. Right. So our moles of KCl should be equal to lowercase m divided by capital M. In this case, it will be 7.46 grams per 74.45 grams per mole. And the grams cancel out. The mole over here is in the per mole part, right? So it essentially goes up. And we get our answer as
0.1002. And the digital point.
0.100201,477. My calculator only goes until 77. Okay, so that is essentially our moles of KCl. Well, what does this mean, right? What does this mean? Let's see what's happened, right? We had 7.46 grams of KCl in our hand. 7.46 grams is the same as that many moles. So essentially, that's how many moles of KCl I have in my hand.
Yeah.
I have a beaker of water. I'm putting it inside the beaker of water, and it is dissolving. As it is dissolving, this is a energy-intensive process. It requires energy to dissolve. Right? That's what it means, right? Why do I know that? Because the temperature decreased. Right? Are we okay so far, everybody? Any questions so far? Okay, so basically, if I'm looking for the enthalpy of this solution, right? Enthalpy of the solution is what? Almost there, home stretch. Right? The enthalpy of our solution is going to be
1.7.
which is the energy.
Yes, energy over mole.
Per mole, right? Exactly.
Energy per mole.
That's how much energy was absorbed, or heat was absorbed by that many moles of KCl. That is essentially what this is over here, right? So this is going to be Q of solution per moles. This is going to be equal to your 1715.44 joules per 0.100201477 moles. And let's do our final calculation then.
That should be kg.
I have my answer in joules over here.
Yes. So,
Yeah, I'll do joules first, right?
okay.
I mean, it's not going to change.
Yeah.
Either do it now or later. I get 17119.90732 joules per mole, right? So let's write down our final answer then. Right? Our final answer statement. What was the question asking for? What is the molar enthalpy of solution? Right? The molar enthalpy of solution of KCl is, now this is where we're going to be careful now, right? We're going to do multiple things over here. First of all, is joules per mole. Let's write it down as kilojoules per mole. So this should be equal to 1, 2, 3. So that's going to be 17.119.90732 kilojoules per mole. Okay, so far? Now, let's convert that into scientific notation, right? So this is the same as writing 1.711990732 times 10 to the power of. It's just moving one decimal place to the left.
1
Kilojoules per mole. Right, so the 4 would be from joules per mole, right? But we've already done the kilojoules part. So we've already moved 3 units to the left. Okay, and then finally, how many scientific, sorry?
None.
How many significant figures do we need?
3.
3, right? So our answer is going to be
1.72.
1.72
Yes.
times 10 to the power of 1 kilojoules per mole.
Oh no, it's 7.1.
It's 711. Yeah, you're right. So I thought it was not here. 7.1.
No.
1.71.
Okay.
Any questions about this? How are we feeling? For sure?
For sure.
Right, you can always review it back on your own time. Let me just erase this part. Okay, so a quick recap essentially, right? Whatever heat is lost by the reaction, right, that's the same as the heat which is gained by the solution. Opposite is also true, right? Whatever heat is gained by the reaction is going to be the same as the heat which is lost by the solution. Right? That's where this whole things comes into play, right? So Q reaction is equal to negative Q of solution. Negative Q solution. And the Q solution is going to be the same that we've seen so far, right? MC delta T. The whole point of this is because the way we're setting up our calorimeter, right, we know exactly what our solution is going to be, right? A, it's an assumption that it has the same density as water, which means whatever milliliters of water I've put, or whatever milliliters of solution that I have, that's the same as the grams of that. Right? 1 grams is the same as 1 milliliters. Density 1. Correct? Right? So that means I have the mass. Right? I know I am assuming that it's like water, which means the C, right? The lowercase c, specific heat capacity, I'm going to use that of water. Right? And I already have a thermometer placed inside the calorimeter, which means I can measure the temperature change as well. Right? So you see how I have the mass, I have the C, I have the delta T of the solution. Right? So that's why this Q solution, you're going to know. Right? And you're going to use that Q solution and do the opposite for the Q reaction to figure out what was the heat of that reaction. And use that heat of the reaction to figure out the enthalpy. Right? That's the step-by-step procedure, essentially, of how do we solve this. Any questions about that, guys? Okay. In that case, let's give this a shot.
What?
Right, we're going to do the same procedure over here, right? We'll break it down, right? First of all, let's read the question. 50 milliliters of 0.300 moles per liter CuSO4 solution is mixed with an equal volume of that much concentration of NaOH, right? 0.600 moles per liter concentration of NaOH. Before we continue forward, let's just see what's happening over here. Right? Let's visualize this, right? Okay. What am I mixing together?
CuSO4 and
All right, so CuSO4 is going inside. What else? NaOH. NaOH is going inside. Right, we're given specifics about these two guys, right? So we're given the volume and we're given the concentration over here, right? Moles per liter is concentration, right? So let's write it down. Volume is equal to 50.0 milliliters, right? Now you can see how that is milliliters, but that is liters, right? So it's a good idea to convert that into liters first. So 50 milliliters is the same as
0.05.
because 1, 2, 3, right? 0.0500 liters, right? Keeping the same significant figures, right? All right, so that's my volume over here. We're also given the concentration of CuSO4 as 0.300 moles per liter. Right? Remember, I showed you guys the triangles, right? There's actually one more triangle over here too that you can use. Concentration, right, is essentially moles per liter. Moles per liter is concentration. Right, so if you have volume, if you have concentration, you can find the moles. Okay, now there is a reaction that is happening over here, right? So it's a good idea to see the actual chemical equation over here, right? So CuSO4 aqueous is reacting with NaOH. Aqueous. What do you guys think is the reaction equal to? What does it produce?
CuOH2 and
Yeah.
NaSO.
Yeah, totally.
NaSO4.
Totally, right? So Cu, right? It's a double displacement reaction, right? Cu goes with OH2. And that's my aqueous plus NaSO4. Na2SO4. If all of them are aqueous, then it's not a reaction, right? So one of them has to be non-aqueous. I'm going to use my solubility table over here. We're working with OHs, right? So it says most of them are solid, which means this right here is going to be a.
Because everything with Na is liquid?
No, not always. Also not liquid, aqueous.
Aqueous.
No, I think what you're referring to is the NO3. Right? Anything that ends with NO3 is aqueous, right? Nitrate solutions. Okay, we're also given something else as well, right? On the other side, we have the specs of NaOH over here. Volume, right? It says equal volume, which means whatever volume you have over here is the same volume over here too. 0.0500 liters. Concentration of 0.600 moles per liter. Any questions so far, guys? Are we all okay? Yeah. All right. Now, this stuff is happening inside a calorimeter, right? So this is essentially the reaction that we have, right? What else are we given? The initial temperature of both solutions is 21.4 degrees Celsius, right? We're given the T I, which is 21.4 degrees Celsius. I think we're given the TF as well, right?
Yes.
After mixing the solutions in a coffee cup calorimeter, the highest temperature reached is 24.6 degrees Celsius. What do you think about the type of a reaction this is? Endo, exo?
Oh, this can be, oh, wait a minute. This had to be endo.
Endo?
No,
Endo means?
exo.
Tell me why?
Because the temperature of surrounding increased.
Yes, right. The temperature of the surrounding is increasing. Where is it getting the heat from? Right? The heat is coming from the reaction itself, right? Nice. Okay. Before we continue forward, let's just make sure our reaction is balanced. Right? So 1 Na, 2 Na, 1 OH, 2 OH. Simple. Let's add 2 as a coefficient of this. Now it's balanced, right? Okay. Thanks. So we're given the temperature change. Determine the enthalpy change of the reaction, then write the thermochemical equation. Okay, well, we know, right, to be able to do this whole enthalpy change part, right, we need to know what's happening in the surrounding, right? We have one piece of the puzzle. We have two pieces of the puzzle as well, right? We know the C, the specific heat capacity, is going to be what? Equal to?
4.1.
Right, because we're assuming that surrounding is water. Yes, right. That's an assumption of a coffee cup calorimeter, right? Yeah. All right. So we have the temperature change. Right? We can figure out the temperature change over here, right? The delta T is going to be equal to TF minus TI. 24.6 degrees Celsius minus 21.4 degrees Celsius, which is equal to what?
3.2.
3.2 degrees Celsius. All right, so we have the C, we have the delta T. What else do we need?
M.
We need the mass of our solution. Right, how do I find out the mass of the solution?
Use
Join is with me, right? Stay with me, guys. Stay with me. Let's think about what's happening, right? Imagine that this is my coffee cup calorimeter, lid, thermometer, and a steering rod. So what did I add in here? I did not add water. Yeah, I added CuSO4. How much? 50 milliliters of CuSO4 is added over here. And then I also added 50 milliliters of NaOH. These are both aqueous solutions, right? Right. So what is the volume inside my beaker? This was 50, this was 50.
100.
Inside this beaker over here, right, there's 100 milliliters of solution. What's the assumption again? Is this CuSO4? Is this NaOH? Yeah. It is. But the CuSO4 and the NaOH, essentially the Cu2 plus, SO42 minus, Na plus, OH minus, they're just particles essentially floating around.
No.
Right? They're just particles, right? Because think about it, these are aqueous solutions, these are ionic compounds. When they are in an aqueous solution, they dissociate, right? And so they are essentially just floating around as ions. Predominantly, however, what do I have? It's kind of like water, right? So if I know the volume of water over here is 100 milliliters, what's the mass?
100 grams.
100 grams. How do I know that?
Because there's
Density. That's an assumption that we make, right? In calorimeter. The assumption in calorimeter is whatever solution you have, right? We're going to assume that it has a density the same as water because predominantly it is water. Yes? Clear with that?
Yeah.
So that means if the density I know is 1 gram for every 1 milliliter, and if I have 100 milliliters over here, that means the mass of that solution should be 100 grams.
By the density, by dividing the mass of a food.
Ideally, yes. But, okay, let's write it out. Can't you find the density by dividing density by dividing mass over volume? You're not wrong. But what am I looking for over here? So tell me this. What is the volume in our example? For each. Right? This is 50 milliliters, this is 50 milliliters. Combined together, the volume is 100. So that means this right here is a 100 milliliters. Right? What else do I have? What do you want, first of all, from this entire process? What is the want? C I have, delta T I have, mass I don't have. What do I want from this equation? I want the mass, right? This is what I want. Anytime you have an equation, how many unknown variables do you need to solve for it?
You need to be the one that is unknown.
Exactly. One equation, one unknown variable. So if this is the unknown variable, I must know what the density is, right? And the assumption in this entire thing over here is the density is equal to what? No, that's the volume in this example. The density assuming, the assumption of density is what? Anybody else? What are we assuming about the density? It's 1. It's the same as water. Water has a density of 1 gram for every 1 milliliters. Right? Why am I assuming that that is water? Tell me. Or why am I assuming that the density of this is the same as the density of water? I haven't put any water, right? I'm putting SCH4, I'm putting NaOH. But why am I assuming that the density of that is the same as the density of water?
Because water is dominating.
Yeah, predominantly that is water. Right? The SCH4, the NaOH, they're just like specks inside.
Yes,
Predominantly is water. So that means it's not equal, right? But it's very close to the density of water. That's the assumption that we're making. So that means this, I also know that is 1. Right? I know that. I want that. So I'm going to move this to the other side, right? So if whatever this is, if I'm multiplying it by 1, it's going to be the same value, right? So that's why if I have 100 milliliters of volume, it's the same as 100 grams of mass. 1-to-1 ratio. Clear? Okay. All right, so now I have the mass, I have the C, I have the delta T. What can I do with that? Tell me. Q of what?
Q of surrounding.
Yeah, in this case, that is the solution, right? This right here is the reaction. This right here is the solution, right? The Q of the solution over here, Dravin, tell me, how do I find that? Equals? Yeah, for sure. But how do I find the Q of solution itself? Like a value-wise? MC delta T. What is the M in this case? 100 grams. Multiply that by, what is the C over here, Drew?
It is 100.
The M is 100. What is the C?
The C is 30. I mean, 3.0.
The C.
Oh. Okay.
4.184 joules per gram degree Celsius. Multiply that by the change in temperature. Mario?
3.2.
3.2 what?
Degrees.
Yes, yeah. Degrees Celsius, right? Eugene, can you tell me, by doing this calculation, what unit will I get left with? What happens here and here? You can show it with your hand. That's great. Yep, they cancel, right? They cancel. What else can I cancel? Temperature, like degrees Celsius. Okay, let's cancel the degrees Celsius. What do I have left? J, joules. My answer is going to be in joules. All right, let's do this. Where's my calculator? All right. Do it, guys. Do it. I need some energy, guys. We're learning about energy. let's get some energy in the system.
Today is exhausting.
I get it, guys. Today is Monday. I get that. But we're almost done. Stay with me. Today is Monday. Yeah, we just started the week. Hey, the good news, however, is this is a short week.
Yeah, no Friday.
Yeah.
I'm gonna be Friday.
No matter. Doesn't matter.
Doesn't matter.
Only one day.
Hey, we just figured out the heat of the solution. Right? What can I do with this heat of the solution?
Then we can calculate the mole, total mole.
Total mole.
No. I don't use. Yes.
What's the relationship, right? Why did I do the whole process of finding the heat of the solution when that's not what I wanted, right? I wanted the heat of the, or enthalpy of the reaction, right? But why am I doing the solution part over here?
Because we have to get.
Are they related somehow?
Yes.
What's the relationship?
Q surroundings equals to negative Q.
In this case, the surrounding is the solution.
Yeah.
And then the other one is the reaction. Right, so tell me, what happens over here? Q solution should be equal to negative Q Rx reaction. Okay, so this means the heat of the reaction should be equal to
negative 1338.8
joules. Fantastic. Hey, but that's not what the question is asking for, right? It doesn't say heat. Right? What we calculated over here was the heat, but we want enthalpy. Right? There's a relationship, of course, right? The enthalpy is essentially how much heat is either absorbed or released per moles. Right? How do I find out the moles over here? Right? This heat that I've figured out over here is the heat of this reaction, right?
So we have to get more.
Yeah, but this heat over here is for a certain moles, right? A certain moles which were used over here specifically. Right? If I had less of this, the heat would be less. More would be resulting in more. Right? It's a relationship, right? It's related to how many moles I used. So how many moles did I use? Is the question. Subtract what?
Times the volume.
Can I find the moles?
Yes.
Right? I have the volume. I know what concentration did I use it at. I can use this section over here to figure out the moles of CuSO4. What's the moles of CuSO4? How can I calculate that? Tell me. I have concentration, I have volume, I want moles, which is so 0.300 moles per liter, which is the concentration. We're going to multiply that by the volume, which is 0.0500 liters. The liters cancels each other out. What do I get over here then?
Something very small.
Something very small? Sure. 0.300 multiplied by 0.0500 equals 0.0515 moles. That's how many moles of CuSO4 I had in here. For that many moles, that's how much energy is absorbed. Absorbed, released. Released.
Yeah, really.
If it's released, which side would I put it?
Right hand, right.
Right, so essentially, I'm going to have something else over here too, right?
Mm.
Right? How do I find out that enthalpy? Right? What is the enthalpy of this reaction going to be equal to? We kind of already know this. We're almost there. Right? That's how much heat is released for that many moles of CuSO4. Divide. Nice. Negative 1338.88 joules for every 0.015 moles of CuSO4 that I have. Now the question is, do I have to use the moles of CuSO4 over here?
No.
Not quite, right? I can use the NaOH as well, right? But you have to mention that, right?
Yeah.
But the general rule is we use the first, right? Whatever comes first, that's what we use. So over here then, 338.88, we can divide that by 0.015, we get a very big number. 89258.66667. Stop it. Stop it.
I did it.
Negative.
I feel that
Predicted.
All right, sweet. But that's a big number, right? Let's make it into a kilojoules over here. Okay, so that's going to be negative. It's going to go 3 to the left, right? 89.258. 666 kilojoules per mole. Right? Mole of what? Mole of CuSO4. And then that's what I'll put over here. 89 point was the significant figures 1 to 3, 1 to 3, 3. Yeah, 89.2. 1 to 3.
Yeah. Done.
Done. Let me just make sure. Yeah. We are good. How are you guys? That's a better question. How are you guys? Okay, I'm going to stop recording, but that's essentially it for today.